Welcome back to another episode of Dave Does Math from Home. Today's topic is other equations. We've already done linear, quadratic, rational. 1.6 is sort of the catch-all section where we do a bunch of other different flavors of equations sort of all at once. These other equations we're going to do are not as commonly experienced as the linear, rational, quadratic ones we've already done, but they're still worth talking about. So we'll cover each of them briefly. The first category is polynomials. Solving polynomial equations is going to feel almost exactly like solving quadratic equations. It's just that the polynomials involved are going to be slightly bigger than quadratic. So, for example, we might want to look at something like x cubed plus 36 equals 9x squared minus 4x. This is an equation. It's got an equal sign in it. It is a polynomial. All of these pieces are coefficients, x's, whole number exponents. It's not quadratic because we got this cube thing here. This one's cubic. But there's still no weird stuff, so still a polynomial. And the plan for these is almost exactly the same as the plan for quadratics. When we had quadratic equations, the plan was get everything on one side of the equal sign so that we can make the whole thing equal 0. And then because things being equal to 0 is very powerful for us, we factored the polynomial and used the zero product property to solve it. So that's exactly what we're going to do here. We're going to move these guys to this side of the equation so that we have x cubed minus 9x squared minus 4x plus 36. And that all equals 0. And because it equals 0, factoring this will be very helpful. And we factor this by splitting it down the middle. So we can pull an x squared out of this first bit, and then we have x minus 9. And we can pull a negative 4 out of the second bit, and then we have x minus 9 again. Because our x minus 9s match, we can factor that out, and we just have an x squared minus 4 left over, and everything still equals 0. This is a difference of squares that we can keep factoring. X minus 9 times x plus 2 times x minus 2 still equals 0. So here we have our solutions. The x value that makes this piece equal 0 is x equals 9. The one that makes this piece equal 0 is x equals negative 2. And the one that makes this piece equal 0 is x equals 2. So we have a cubic polynomial. We have 3 solutions. It checks out. Since we've already spent a long time factoring cubics, and we've already spent a long time setting things equal to 0 to solve them, that's really all I'm going to say about the polynomial side of this. It's 2 things we already know how to do. You're just putting them together. Set it to 0, then factor. Let me write that down. Set it equal to 0, then factor. Same as the quadratics. The next flavor of function I want to talk about is radical functions, which sounds really cool if you're from the 80s or 90s. Radical equations, radical is the fancy math word for this symbol. This is a radical. That's the radical symbol. the square root symbol. So sometimes you get these radical symbols in equations. Sometimes you get things like x minus 6 or x plus 6. The square root of x plus 6 equals x. This is a radical equation. It is an equation. There's a radical involved and some x's. For these equations, if the radical is by itself, all you have to do is square both sides. When you square the square root of a thing, you just get x plus 6. And when you square this, you get x squared. And that works out nice. And now that the radical is gone, what we have left is a quadratic equation. And we know how to solve those. You move everything to one side so that it equals 0. And then you factor it. So it should be x plus 2 and x minus 3. Those are the factors. If these are the factors, then the solutions are x equals negative 2 and x equals 3. Here's where these get a little bit tricky. We have to be really careful about our solutions to these problems for the same reason that we had to be very careful of our solutions in section 1.2b. In 1.2b, we dealt with rational equations. And every time we got solutions, we had to check them because those equations have domain restrictions. There are certain x values that aren't allowed. This is sort of the same. And it's sort of made worse by the fact that we're squaring a thing. So one of the things we have to check for is if you plug this number in, are you going to create some sort of illegal square root situation? And in this case, I think that we're not. If we plug in 3, that'll check out. If we plug in negative 2, you're either getting the square root of 9 or you're getting the square root of 4. Both of those things make a certain amount of sense. The other problem is, though, these things might not always work because we're squaring things. Here's how, let me explain. When we plug in x equals 3 into this equation, we have the square root of 3 plus 6 equals 3. And this is true. This means that the square root of 9 equals 3. That's good. Everyone is happy. If we try to plug in x equals negative 2, you get negative 2 plus 6 equals negative 2. So the square root of negative 2 plus 6, that's the square root of 4, equals negative 2. This is not true. The square root of 4 is not negative 2. This radical always means the principal or the positive square root. So the square root of 4 is positive 2, it's not negative 2. So this is not a solution, it doesn't check out. This is a false solution that got introduced because we squared the thing. Once you square this equation, like if you square both sides of this, like we did in the first step of solving this, then it becomes true. If you square the negative 2, then it equals this. Both sides become positive. But without this square happening, the solution process is going to give you positive and negative answers when this only can really accept positive answers. That's sort of an oversimplification. The moral of the story is check your answers. Whatever kind of answers this thing gives you, you have to check them in the original equation because radicals do crazy things. Squaring both sides of an equation can introduce false solutions that they solve the squared version of the equation because squaring the equation makes everything positive, but they don't solve the original version of the equation because there's a positive and negative mismatch. That is the big advice here in the takeaway. There will be a quiz where solving this equation gives you two answers, and one of those answers will be incorrect. And that'll happen on the exam as well, and then again on the final. So paying close attention to which solutions are correct and incorrect is pretty important. I'm going to do another one of these so we can look at what that looks like with a little extra step involved. So the step that we just did is square. The step that we just did is actually step 2. Square both sides to eliminate the radical. That is step 2, and we started with step 2 here because we were allowed to sort of skip step 1. I'm going to do another example where step 1 is not skippable. It is the square root. No, I don't want to put it there. The square root of 2x plus 5 equals x. If we try to square both sides right now, we will get a terrible, horrifying mess. Because if you square this, this has 2 pieces. That means you have to FOIL them. And you'll end up with 4 different pieces. You'll have the first thing squared, which will be nice. That'll cancel the radical. And you'll have the last thing squared, and that'll be the 25. That'll be nice. But there'll be 2 middle pieces that both have a radical in them. If your goal is to eliminate the radical, squaring this right now will not accomplish that because you'll have to FOIL things. Which brings us to step 1. Isolate the radical. So before you do anything else, make sure that the radical is by itself. Once you have an equation like this, now the radical is by itself. Now, squaring both sides of the equation will, in fact, eliminate this radical. We'll just have a 2x plus 5 equals... No, you have to FOIL this part instead. So we still have to FOIL something, but this is much easier to FOIL than this is. This will give us an x squared minus 5x is minus 10x, and then plus 25. Not so bad. No more radicals, at least, and that's the goal. The radicals have been eliminated. And now, again, we are left with a quadratic, which is fine. We can solve quadratics. We have lots of practice doing that. We just need to make sure that both sides become 0. So we subtract the 2x from both sides. And that gives us minus 12x here, and then we subtract the 5, and that gives us a plus 20. Now I need 2 numbers that multiply to 20 and add to negative 12, and that's probably x minus 10 and x minus 2. So I get, let me come over here, say x equals 10 and 2. And as usual, we have to check these. So I'm going to plug them back into these guys, and we'll see what's going on here. I'm going to plug them back into the original. When you plug in 10, this looks like the square root of 2 times 10 plus 5 equals 10. Is that true? 2 times 10 plus 5 is 25. Square root of that is 5. Plus 5 equals 10. Yes. That one checks out and is happy. If I plug in 2, Square root of 2 times 2 plus 5 is 9. Square root of 9 is 3. 3 plus 5 is not the same as 2. If you subtract this 3 from both, if you subtract the 5 from both sides, then you would get something like this. This here would be -3. And then we kind of see this positive negative thing going on. This is still the square root of 9. It's trying to tell us that that's -3. That is a false solution that got introduced when we squared everything and made everything positive. But it's not an actual solution to the problem as written. One last note about these radical equations. When you're doing a test or a quiz, I want to see all of this work. I want to see you isolate the radical. I want to see you square both sides and FOIL it. I want to see you set one side equal to 0 to get a quadratic, and then you factor that, get your 2 answers, and check both your answers. Because of the way this class is structured, it is sort of possible to kind of look at this and think, what numbers could be nice little square roots here? And because like there's not many perfect squares that are reasonable size numbers. So you could say, can I make this the thing in the radical? Can I make it equal 4? Can I make it equal 9? Can I make it equal 16? Can I make it equal 25? You can kind of just go through the list and like figure out which x values would work. I don't want to see that on test or quizzes. That only works on these problems because I'm very intentionally using small, easy to work with, simple numbers. If you were to encounter a problem like this in the wild, in industry somewhere, it would not have easy to work with numbers. It would not have perfect squares. I want us to understand the process of isolating the radical and squaring it to get these answers outside the realm of nice, easy numbers. So guess and check is, I mean, I guess I can't stop you from doing guess and check, but if you do one of these on a test or quiz and the only work I see is a guess and check, like I think that this should be 25, so I'm going to make x equal to 10. If that's all the work I see, then I'm not going to give you any credit for it. So that's it for radical equations. There's one more type of equation we need to talk about, but I want to put it in a second video. So that's going to be it for this one. Stay tuned for part 2.